Okay, in our video today, we're going to talk about the idea of domain and range, and we're going to start by doing that with some parametric equations. Okay, so parametric equations, the idea is there's normally a rule about t, and we've got to see what happens in this equation and this equation. Okay, what happens with the x, overall, we will call these results that we can get the domain, and we will call the results that we get from the y1 the range. However, you can kind of sort of break them down into their own parts by thinking about x and y and then bring them together at the end. So a trick that works quite well to start with is taking these values on the left and the right and plugging them in and seeing what happens. So let's do the x equals first. So it says that t has to be bigger than 0, but what we're going to do still is we're still going to think about what happens when x itself is 0. And what's going to go on here is this is sort of like a natural log graph. Natural log graph normally goes something like that. So I'm just going to sort of roughly draw that on. Okay, so if I put x equals 0 in, that would give me, wouldn't it? That would give me the natural log of 2. And I know I'm not allowed that value, but it's still going to be a useful value. Now, I can see from my sketch that if I use a bigger number, like 2, I feel like I'm expecting a bigger answer. So I sort of know which way the inequality goes already. And if we put in x equals 2, we would get the natural log of 4. Now, if we're going to make sure we don't drop any marks at all, this one we have to just be aware is actually not included, whereas this one here is included. So for the domain, just the domain to start with, what we could do is we could say that we are starting at the natural log of 2 and its value is bigger than that. Domain is about the x values, and it's up to, and it's including the natural log of 4. Okay, we haven't done anything at all with the y yet, so let's do the y part now. So the y part's the range. So if I do a very rough sketch, e to the something, sort of looks like that, doesn't it? 0, again, is a value I want to think about. Well, e to the 0 would give me a 1. And that's another value that is of interest, but I can't actually include that value. So I'm going to say bigger than 1. Why bigger than 1? Well, I can see from my sketch, as I go to the right-hand side now, I'll be going up. 2, so I'm going to leave it in exact form. It's going to be e squared. Okay, so there's kind of a quick illustration of this idea that you take the values of interest in the question, you plug them in, and then you're just really careful with your inequalities. Let's do another one. So here we've got sort of a trig example. So x equals y equals, and we've got our restriction. So what we could do to start with is for the domain, why don't we do a very rough sketch of a cos graph, okay? For sine, it does say sine 2t, which will mean that the graph's more compressed. However, I'm going to just start by drawing the rough shape to get me started. Now, if you were to do the whole thing normally, all of this is 2 pi or 360 degrees. And you can see from this restriction here that it's much, much smaller than that. So I definitely won't be able to use all of these values. And because I can't use all of these values, it means I won't be able to get all of those values. So if you limit what t can be, you'll find that you'll limit your domain and your range as well. So pi over 3, well, where would pi over 3 be? That's 60 degrees is the equivalent. So I'm effectively saying that it's only this part here, and everything else wouldn't be allowed. So can you see that that's going to restrict what x can be quite a lot? If I put in the 0, cos of 0 will give me 1. So 1 is definitely involved. And then as I go to the right here, the values are going down. So 1, and it can be 1, and less than that. And what's the smallest value? Well, the smallest value will be here, which will be cos of pi over 3. And if I do cos of pi over 3, I'll actually get an answer of a half. So that would be my domain, and I actually have to include both. So let's write that a little bit more neatly. Yeah. So the rule for the domain on here is going to be that it can only be between a half and 1 inclusive. Yeah. So even though it's cos, you can't get answers like 0 or -1 here because we're being so restrictive with this one here. Well, how about sine? Let's do the same for sine. So 0 is where it starts at 0, isn't it? And you have pi over 3. However, because you've got 2t, it's like 2 pi over 3, okay? Which is a bit further on than it would normally be. So it would normally be sort of about here, but because it's double, you're going to find that the part that's used is sort of about this part here, okay? Sorry, correction there. The part that you would normally use would be up to here, so it's going to go up to about here this time. So what you're going to do is you're going to find that it occupies that part there. Now, if you put sine 0 in on your calculator, you would, of course, just get 0. And if you had put sine of, what's that? If you had put sine of 2 pi over 3 in, you'll find that you'll get yourself an answer of root 3 over 2. However, that's not actually the answer here, is it? Because we're finding sort of the widest range of values that you can get. And can you see that that's actually here at 1? So although you get the 0, which is part of the correct answer, the root 3 over 2 is slightly misleading because it's only picking up on that value there. It doesn't show you what's happened in between. So doing a sketch and thinking about where graphs have turned is quite a valuable exercise. So 0, and we can have the 0 because of that type of inequality sign. I'm going to write y, or you could write f of x. And it can go up to and including 1. So just one to be slightly wary of there, that you need to watch spots between where things may have turned around. We'll do one final one of a slightly different style with domain and range just to finish. So on this one here, we're going to start with a quadratic. So what will we do to start with? Well, if you look at part A, they want us to complete the square. So if we complete the square, this is one way that you can do it. You can take a 3 out, leave an x squared minus 2x there, and then a plus 12 on the outside. If you are completing the square, I would recommend doing it this way here. So half is going to be x minus 1 squared, and then I'm going to take away 1 squared, which is just minus 1 in this case. So let's just tidy things up now. So I'm expanding that back. I'm doing this one. Don't forget to do this one as well. So that's going to be a minus 3 plus 12. So let's just call that plus 9. Okay, so 3x minus 1 squared plus 9. Now, on the next bit, I need to draw it, showing carefully any points of intersection, and then need the coordinates of where this graph turns. So having a completed square makes that much easier. You can see some details from the original, such as the y-intercept being at 12. You can also see that it's a positive x squared, so we know roughly the shape that it's going to make. But the completed square is quite useful because it tells us that this is going to turn. So at the opposite here would be at the point 1, and then you just take this value as it is. At the point 19, this graph will start to turn around. So as a sketch, it would look roughly something like that, where 19 would be the turning point. Okay, there are no roots. You can see that there's no roots because it's turned around before it's gotten to the x-axis. So we are done here. We are done here. Sometimes they do want actual coordinates rather than points. So I'm going to do that just to be safe. And what do they want? Describe fully the transformation that maps f of x onto f of x plus 2. Well, how do you get from f of x to f of x plus 2? Well, this here is a translation. It's a translation because it's in the form plus minus. It's a translation of, well, it's inside the function, we say, so it's sort of in the x direction, and it sort of does the opposite to its notation. So that would be a translation of 2, 0 for that one there. Finally, what's the range of a function which is described as 1 over f of x being what we've just done? Well, if we consider f of x, let's just think about the range of f of x for a minute. So from our diagram, we can see that it's allowed to be greater than or equal to 9, isn't it? Okay. So what's going to happen when we put 1 over f of x in here? Well, we're going to be doing 1 over numbers such as 9, 10, 100. So just think about what's happening here, and you'll see that 1 over 9 is actually the largest value that this can be. So for h of x, it's a ninth is the greatest value that it can achieve. And what's happening when I do 1 over 100, 1 over 1,000, so on like that? Well, it's getting squeezed and squeezed and squeezed, this value, closer and closer to 0. Can it actually be 0? No, it cannot. So the final part there, the range of this function would be as follows. So we've looked at in this video taking information in the question and inspecting those values to find our domain and range. But sometimes we have to use turning points, and it's not always as easy as copying the inequalities to know what might happen. We do need to sketch, and we do need to reason our way through this.